Hi everyone, welcome to this course, the Introduction to Statistical Mechanics to Software and Automated Systems. So far we have studied about Brownian dynamics and we see how 1D random walk leads to different situations, and we used different statistical tools to see how random walks, those kind of random walks will be useful in different problems. So we worked out few examples about about physical systems and also different systems, and we tried to use uh, our random walk models, and we tried to use the insights that we got from random walk, uh, and we have used it in those problems. So, and in the last class, we sort of talked about how the Brownian dynamics will be changed if we introduce some external potentials, and we uh, basically solved for a simplest possible potential, which is a harmonic potential, and we solved for that, and we got the mean square displacements, we got the time correlation functions and all these things. So today we will continue our discussions about the Brownian dynamics, and basically this Brownian dynamics, basically this is due to the thermal motions, right? You understood from the random normal random forces that these are due to the thermal collisions. Okay, so today we will see, so far we have discussed the shape of the particle is spherical. Today we will see that if the shape of the particle is different, how those things will be changed. Okay, so let me share my screen, just a minute. Yeah, I hope you can see my screen well. Okay, so we will, so far what we know, that we know about the Brownian dynamics for the spherical particle. So we basically solved for that, and we also got to know the uh, uh, drag, viscous drag about the spherical particle and all these things. So now today we will continue our discussions about for general shape. Okay, so we what we will do now today is, so you will get all these notes and all these things uh, in your course platform. So so far last time what we did, we calculated for uh, harmonic potential. So what we did is we sort of introduced the this so this is the external force due to the uh, uh, external force due to the external potential that is being added. So this is the inertial term, this is the random force, this is dissipative term, and this is the external force. So now, and this random force is due to the thermal motions or like thermal agitations of this, the media they are in, and we sort of knew that the random force is given by the Gaussian variable, which is similar to the free particle. By means, what we are trying to say is this random force does not depend upon that what is the external potential if we introduce. Okay, so basically that's that. And and that is what we have written here, that this is precisely because the random force is determined by the thermal motion of fluid molecules, and it will not be affected by the potential of any form that has been there. Okay, so and also we here we assumed few things, that since velocity autocorrelation time, which is m by gamma, is very small compared with the characteristic time of the Brownian particle, which is few milliseconds, and we can consider the limit that tv, which is autocorrelation time, is tends to 0. That means it's very small, we can consider it as 0. Now in this limit we can safely ignore the inertial term, because since it is around that very small limit, and this is also in the, so viscous drag dominates in this region, so this is this thing. And so in this equations this term will be 0, so this will be 0. Sorry, this will be 0. So now if we if we sort of arrange these things, we will get this kind of equation, right? And we uh, made a certain variable out of random force, which is called random velocity. So random velocity is responsible for, so the random velocity is like random velocity imparted by the molecules by, which is acted by the random force. Okay, so so similarly, this random velocity, autocorrelation of the random velocity, that will be, you know that will be written accordingly, because we know the relation for the random force, autocorrelation of random force, which is 2 gamma kVt delta t minus t prime. But since random velocity is forced by 1 by gamma, so there will be 1 by gamma square will be multiplied, so 2 gamma kVt by gamma square, so you can get 2 kVt by gamma. So and now we written, so since we have also in the Einstein relation, where we have connected the fluctuating part with the dissipative part, and we have written the fluctuation dissipation form, so we can here write that this is diffusion coefficient. So now we can also get that this is a Gaussian random variable, which can be characterized by this mean 0, and the autocorrelation of time autocorrelation thing will be 2d delta t minus t prime, which is obtained from here, right? Now here we can get that correlation of the fluctuating velocity is equal to the correlation of the free Brownian particles velocity. This is expected because the free Brownian particle velocity is mainly due to the given random force, because that due to the dissipative part it ultimately dies down, right? So and this needs to be the case because the fluctuating velocity is independent of the external potential, right? Now we have considered the harmonic potential, because any irregular form of potentials can be thought of a harmonic potential around its minima, which we have of which can be obtained from this Taylor expansion. So now if we write these Langevin equations in the presence of harmonic potential, well, then it boils down to this. And now since we can get the harmonic potential ux is equal to half kx squared, from there we can get del u del x, which is half kx squared del x, that makes it kx. So we can get these equations del dx dt is equal to minus x by tau via t. And then we solve these equations to get xt and x0, and there we got the autocorrelation function of x when in the presence of harmonic potential, and we got this form. And this term is 0 because x0 and this random fluctuations, that makes it 0. And the probability distributions is actually obtained from the Boltzmann distribution, because if you know the Boltzmann distribution, so if you know the potentials, you can get the probability distribution, or if you know the probability distributions, you can always get not unique, you cannot get the unique thing, so but you can get a certain term which is varying with x, and from there we got that x naught square is kbt by k. So that means the this initial conditions, if you sort of get t equal to 0, that should be, because that is also, that can also vary, because we are talking about the statistical mechanic descriptions, so that can also vary. So this initial condition t equal to 0, these initial conditions, if you take their square and mean, it is kbt by k. So now we can get this kind of, and we got these time autocorrelations like this kbt by k, k, this is the restoring force constant, e to the power minus mod of t by tau. So this, you can see, this is similar to the Brownian motions, where we have we didn't neglect the universal term, and from here you can get the mean square displacement like this, which is like in the negative and positive directions behave like this. So it reaches a plateau region due to this exponential function. So this is kind of a, you know charging thing. Okay, so also like velocity of correlation function can also be calculated from this expression. So if you calculate it, then from here you get this, and you get 2d delta t, there is a delta function minus dt by to the power minus t by tau. So you can get at this region, at very smaller region, it will be determined, the main thing determining is this delta functions, and then it will be exponentially, uh, uh, like the exponential functions that we have written earlier. Okay, so since now we defined all these things, let's start our new topic. So today what we will discuss, basically, Brownian motion of particles of general shape. Okay, so if you write, then Langevin Langevin equation for particle configuration. So now what we will do, we will write the Langevin equation for any shape of the particle. Okay, so now you know that, let's say, a rod like shape. First we will talk about the rod like shape. Okay. So consider the Brownian motion of a particle of general shape. Okay, so we are talking about general shape. Let's say rod shaped. Okay, or collection of those things. Now this configures of any kind of shape that can be considered that can be actually sort of described by a set of generalized coordinates, right? So any kind of configuration can be described by a set of generalized coordinates x is equal to, let's say, x1, x2, x3, like similar to the case where there was, like, for Cartesian coordinate, this generalized coordinate will be x, y, z. For spherical, if this, let's say for rod shaped particle, this will be like cylindrical coordinates will be useful to consider, right? So there it will be r theta or r phi z or rho phi z, like this. So let's say configuration of configuration of a rigid particle is described by six coordinates, because by positioning it's like three or representing the position and three representing orientation. So from there you can get six coordinates and you can talk about that. Okay. Okay, so let's say such particles are moving in a potential. Okay, so now again consider such particles are moving in a potential field ux. Now the Langevin equation for this situation, so the Langevin equation represents the balance of three forces, right? Represents the balance of three forces, because you see here there was four terms there was four terms: inertial, dissipative, external force, and random force. But inertial term can be zero because this is in low Reynolds number regime, because the time autocorrelation autocorrelation time, velocity autocorrelation time is very small, so we can neglect this inertial term. So only these three external forces remain. These three forces remains: dissipative force, external force, and random force. So we have to balance these three forces to get the equation of motion, or Langerman equation, right? So if you get these three forces first, namely, I will namely write those things. First, the potential force, the potential force, which is Fp is equal to minus du dx, the frictional force, is minus gamma x dot, and the random force, and the random force. So the random force is, we know about, we talked about it in great detail. Okay, so now we will write this general case. So in general case, the potential force, the potential force is defined is defined by the change of the potential ux, right? Because it is like the change, how potential is changing is like the force, right? When the particle is displaced by an amount dxi. Remember, these are like not the simple coordinates, these are like the displacement coordinates, generalized displacement coordinates. So then du is equal to minus I fpi dxi, because this is a p, it stands for potential, so this is 1, and then therefore we can say fpi is equal to minus du dxi, this is 2, where fpi is called the generalized potential force, potential force conjugate to xi, because force and the variables are like conjugate pairs. So what is this is like conjugate we call force. Any generalized coordinate and its force, they are called co conjugate variables. So this FPI actually a various force depending upon the this coordinate. Let's say this is r, then this will be F potential r, because this is in the radial directions. If it were theta, it would be F theta I, that means the force along this theta cap directions. Okay. So let's say if it is, so r was the normal positional coordinate, that's why it is force. Let's say if it was angular coordinate, then it would be torque, right? So torque force, they are in generalized sense they are called generalized force, but individually they are called like torque or like force, whatever in our like school days what we talked about. Okay. Now another thing is remains, that is frictional force, right? Let's come next comes frictional force. So this frictional force F subscript Fi, that means small f is the friction, I is the that coordinate, if capital Fi is generally generally defined defined by the irreversible irreversible work W air due to the irreversible work, which who done this work, like done to the fluid done to the fluid per unit time when the particle the particle is moving moving with with velocity x dot is equal to x1 dot, x2 dot, x3 dot. Okay, so basically this thing. So now if that is the case, then W W irreversible is equal to I F F I X I dot. So this is called equation number 3. And also this frictional force is a linear function of the generalized velocity. So, and also frictional force if Fi is a linear function of x dot, which is velocity ob- obviously for that, you know, of that directions and of that coordinate, and it is written as if I is equal to minus j gamma ij. So remember, now this becomes this becomes not a constant, this is becomes a generalized friction coefficient, and this is a matrix. Okay, this becomes a matrix. Okay, so this, please be careful when you consider these things. And where gamma ijx is generalized friction coefficient friction coefficient friction coefficient. Now generally, now this frictional force, this frictional force Fi, which is conjugate to xi, generally depends on the velocity of other coordinates. Xj dot. So means like, if it is moving like this, then what is the normal velocity, normal direction to that? That would be more important. Okay, so which can be seen here. Let's say this is a generalized object, and let's say so if phi is in this direction, so frictional force it's in this direction, this will be torque. Okay, tau f, like this. So need not be in that directions. Okay, so it should be like this. So let's say a particle which is moving, a particle, this is a kidney beans kind of a thing, a particle, let's say bean like particle. So the particle, then it, if we see this bean like particle, where moves it moves in the x direction, x direction, and the the frictional force capital F, F, small f, always not p, will not be parallel parallel to the velocity vector, to the velocity vector. Okay, because you know the the motion in x direction will induce a frictional force in the y and z direction. And also this translations, also on top of this, also translational motion translational motion of such a particle will induce, because this is a asymmetric particle, will induce a frictional torque too, a frictional torque Tf2. These can be calculated hydrodynamically, and we can, you know, go details into this, but that will be in a fluid mechanics. So let's just not go into this. So now we will come back to the Langevin equation for the generalized coordinate. So the Langevin equation for generalized coordinate then it becomes minus average over j gamma ij xj dot minus delta u del xi plus if rit is equal to 0. So this is a random force for the generalized, you know, coordinate. And this random force, this specific random force, so this is 4, this is 5, and this random force satisfies the same equations that we talked about earlier, right? For let's say its mean is 0, and if you talk about its, so here there will be two kind of correlation. First the time correlation, then is also like the space correlations too. So there will be, if you talk about two directions, so there comes two gamma ij. So now this is this gamma, it was earlier was a constant for spherical particles, but this asymmetric particle, this is a, you know, this is a metric. Okay, so now to gamma ij kbt delta of t minus t prime, so this is 6. Okay, this is the generalized equations. Okay, now so this can be actually, this can be derived from first principles, but we will not go into this because we have to discuss a lot in this course, and this will be much more deeper things, because the main purpose of this course is to sort of give you some overview. How can you get the ideas? So because these are sort of creating a base so that you can get into, you can, so that you can get into the course sort of understanding that what is actually required if you want to do some kind of uh, research in today's time in, let's say theoretical physics, or experimental thing, and this kind of description is needed. So that's why this kind of statistical tools we are discussing now, and that will give you some sort of a platform, and you will start from there. Okay, so this is the motivation of the course if you talk about the main thing. Okay, now the reciprocal relation. This is now this friction coefficient have some following properties. So please look into these reciprocal relations, you know, carefully, because if you understand this reciprocal relation, then you will understand the how the life at low Reynolds number is completely different from high Reynolds number. Let's say how we, like the human beings, we swim in the swimming pool, how our fate in swimming is completely different from like a certain species, like small species that is swimming in pool, because its fate, it's completely related to its size, like how its size and speed sort of making it uh, obvious to be to be in that pool. So so you, if you are very much more curious about it, you can go into these things. Let me discuss it, and then we'll talk about that. Okay, so first is, gamma ij, this matrix X, is symmetry. Symmetry. That means gamma ijx is equal to gamma jix. So this is symmetric. Okay, first. Second is the matrix of gamma ijx is positive definite. Is positive definite. That is, that means for any xi dot, we always get gamma ij x xi dot xj dot, and it is added over I and j, will be always greater than 0. This is positive definite. This relation, first relation, this one is sometimes called Lorentz reciprocal relation in hydrodynamics. Now these reciprocal relations, if you think that this is very trivial, this is not very trivial relation. It has some greater implications to think about. Okay. So first is that if you think about the situations when a particle, let's say, moving in x directions with velocity vx, okay, so if it is moving in x directions, the hydrodynamic drag generally involves y component, right? Let's say you are talking about a 2D relation. So if it is moving in x directions, the velocity drag will affect, or like particle velocity drag actually involve the y component, that fy, and conversely if it moves in y directions, the velocity will be in vy, and that's why the hydrodynamic drag involves fx, right? Now velocity, okay, this is the greater equal to 0. Now this velocity autocorrelation, sorry, this reciprocal relation indicates then that the cause and the effect, their ratio, that means f fy by vx and ffx divided by vy, they are equal, which is not trivial, which is not very much trivial, right? Let's say take a example of helical shaped particle. Like for such particle, the translational velocity v, which is like that helical shaped particle is moving, so the translational velocity will create a frictional force which is, let's say, a frictional torque. Similarly, a rotational velocity will create a frictional force, and these reciprocal relations give the identity, like, so for velocity it is becoming torque, and for angular velocity it is coming out to be a frictional force. So this is like a, it's not very trivial, right? Okay, so basically what we are trying to mean here, what we want to say that let's say a particle is moving in x direction. Okay, okay. So the particle is moving in x direction. So with velocity, let's say with velocity vx. Okay. Then the hydrodynamic drag, the hydrodynamic drag generally involves a y component. So this involving this y component. So now you will see that if the particle is moving in x directions with velocity vx, so the hydrodynamic drag that will involve y component, let's say if y, and when the particle moves in the y direction with velocity vy, then the hydrodynamic drag involves an x component f fx. Okay. So now the according to the reciprocal to the reciprocal relation, it will be that f of fy divided by vx is equal to f of fx by vy. Okay. So basically, what we are doing here, we're writing this equation 7 as like this. So that is what we are doing here. So basically we are saying these drag coefficients are sort of similar. Okay, so it is not very trivial then, huh? So this is not, which is non trivial. Now Onsager has shown that the relation reciprocal relation can be proven can be proven without invoking hydrodynamics. Actually, Onsager derived the reciprocal relations for kinetic coefficients in irreversible thermodynamics, but the proof that he did is the same as that we will discuss here. So here the proof will be adapted to the Brownian dynamics. So what he took, his main idea was his main idea was time reversal symmetry of the time correlation function at equilibrium Okay, so now since these coefficients, so he mainly took the help of time reversal symmetry, so that is his main weapon. So since the friction coefficient J depends on the particle configuration, which is denoted by the general coordinates configuration x only, and it is again coefficient, and it is independent of the potential u of x. We can take the special case we can take the special case that the particles are subject to a harmonic potential like u of x is equal to half ki for each coordinate xi minus xi0 whole squared. So this can be termed as equation 10. And the configuration particle configuration cannot deviate significantly from its equilibrium, or like from the equilibrium configurations significantly from the equilibrium configuration let's say x naught, which is x1 naught, x2 naught. In this case equation equation 5 can be solved for the deviation or fluctuation from its equilibrium point. From the deviation, let's say epsilon I t, which is xi at t minus x naught I, then the requirement that the time correlation function let's say epsilon I t epsilon j 0 is symmetric with respect to the exchange of I and j gives the reciprocal relation. Similarly, because then you will get the reciprocal relation will be like this, because there you will get xij like this term. This will be time correlation function, so this will be like this, just from previous discussions. This will be like this. So there will be constant term So this term then will be changed. Just a minute. So just a minute, I'm just trying to connect this. So what I was saying is, so you just need to say that if you talk about the deviations of this variable, generalized variable, from from its equilibrium positions like this, then you can get the time correlation functions like this of this deviation. If it is symmetric with respect to exchange of I and j, that will gives you the reciprocal relation. So by this, you get this discussion. So basically what Onsager did is, Onsager actually derived the reciprocal reciprocal relation for the kinetic coefficients or mobility parameters, kinetic coefficients in irreversible irreversible thermodynamics thermodynamics but here the essence of proof is same as the original one. What we did is that here we have presented it in a form adapted to Brownian particles. Okay, so that is what we are doing here. Okay, so now what we will do, we will prove the fluctuation dissipations uh, in for a generalized form. So let's get this time correlation of generalized random forces. So that is what we will do. Okay, Okay, so let me start the discussions. Now, statistical mechanics, in the beginning we talked about, it actually describes like any system as a dynamical, systems which consisting of the, microscopic, variables, and from that how that macroscopic phenomena are happening, that we can comment about. So statistical, so there the Hamiltonian's equation of motion plays an important role. So statistical mechanics regards regarding any dynamical system, any dynamical system follows a certain degree of Hamiltonian's Hamilton's equations of motions, equations of motion. Okay, now if we know the Hamiltonian of the system, we can sort of predict the time evolution of the system, which can be calculated by solving Hamiltonian's equation of motion. So if we know, if we if we know the Hamiltonian of the system, Hamiltonian of the system, just a minute. So if you know the system, so if you know the Hamiltonian of the system, then you can easily talk about the how its time evolution. So system time evolution of the system can be calculated by solving Hamilton's equations of motion, equations of motion. Now the Hamiltonian of a system is not every time, it's not very easy to say, right? Let's say it can be written as h is a function of the system variable, and it's where represents the set of coordinates, the set of coordinates specifying its position, specifying the positions and momenta momenta of all the molecules in the system, all the molecule in the system, and x is equal to x1, x2, xn. they represents they represents external parameters, external parameters parameters which can affect the molecules but can be controlled externally, right? So which appear in the Hamiltonian, which appear in the Hamiltonian. Now our aim is to sort of get the, so now our main job is to know how our job is to get fluctuation dissipation dissipation theorem for this general definition definition of x. For this general definition of x, we got to do this. Now, what is the relevance of this theorem? So, for that, we are explaining the theorem for the systems of the Brownian particles. Now, for the relevance of the theorem, because we are studying the Brownian particle systems theorem, clearly we are explaining we are explaining the theorem the theorem for the system of Brownian particles. Okay. Now, for Brownian particles, it is sort of thought about a macro particle or big particle. So let's say consider a big particle or particles, because or particles, you can think about more particle, but that number of that particles which much lower than the molecule number in the solution, okay, or placed in a fluid, okay, in a fluid. and regard this omega as the lambda as the coordinates specifying coordinates specifying positions and momenta positions and momenta of the fluid molecules fluid molecules. Okay, and the x, which is x1, x2, x3 dot dot as the parameters specifying specifying the configuration of Brownian particle. Brownian particle. Okay. Now here we are considering the system made of fluid molecules only. Okay. So and the configurational parameters x of the Brownian particles that are regarded as the outside parameters or external parameters in Hamiltonian for fluid molecules. So here for the x, which is the of for Brownian particles, which are thought of as external parameters. So now forces acting on the particle, so you can think of it as, let's say, it's a big let's say there are this kind of, let's say, copy it. So let's say this is here, this is here. Again, so this is there. So now you sort of, let's remove this and you insert this Brownian particle like this. So this is the Brownian particle. So this is moving in these directions. Now here this particle is our Brownian particle. So this is, let's say you talk about this. So this variable, let's say this is the center of this. So one day motion, let's say that this will be the xt. It's how it is moving like this. So how it is changing its directions, that can its positions, that will be, sort of decoded here. So now the forces acting on the Brownian particles can be given as So the forces acting on the Brownian particle are given by, let's say this, let's say if I is equal to minus delta H of delta Xi. Okay, so let's take the equation number as 11. So let's say this is equation number 11. Okay, where where if I x represents the instantaneous the instantaneous force acting on the Brownian particle, which we denote as pp by fluid molecules by fluid molecules which are in state microscopic state, because they are changing very fast. Okay, now we want to know the macroscopic quantity, right? So the macroscopic force, let's say the macroscopic force at time t is the average of this microscopic force. So if this is the so this is like similar, this force is, it is actually, this is the generalized in Hamiltonian's principle, so we can take it from here. The macroscopic force at time t is the average of this microscopic force, which is f I of this one x, for the distribution functions, because we have to know the distribution functions, because whenever we are taking some average of some quantity, we need to know what is the distribution is follows. So the distribution function, let's say this is psi of this variable x and t, right? So if you take it, then this becomes f I of t is equal to, like, taking average over this whole space and of this quantity, and we need to write the distribution function, which is this one x t. So if we know this, then you can easily get the other things. So now what we did, we sort of got got in our hand the microscopic force, and from microscopic force we can easily get this macroscopic force by taking the average. Okay, so we will stop here. We will continue our discussion in the next class, next discussion session, so that we can get the fluctuation dissipation relation from the time correlation of generalized random force. Okay, so I'm stopping here.